Aquabiz, all the best knowledge for aquatic system.
Sawadika. It is my pleasure to be here in Bangkok this morning, and I would like to thank USEC for this opportunity. I always enjoy coming here in Bangkok, whether for personal or professional visits. I made many friends here in Bangkok when I was then working with the CIFDEC Aquaculture Department. This morning, there are many interesting things that we can talk about tilapia, but I think you know more about tilapia than I do. However, please indulge me and bear with me because some of this information may not be new to you, okay? So let's probably just revisit some of the things that we do when we do rootstock development. Okay, it's okay, just a minor technical glitch. As you can see from the slide, aquaculture is indeed the fastest growing food sector. In fact, it has been increasing through the years, and aquaculture actually is now like more than 50% of human fish consumption globally. In fact, in 2018, it was estimated to have this production 114.5 million tons in live weight, with a farm gate sale value of about 263.6 billion US dollars. So there is a very great potential for doing aquaculture. Yeah, maybe just there. Okay. The slide is showing us the status of Nile tilapia production globally. It now ranks as the third major species produced in world aquaculture. And tilapia also has been increasing yearly. Okay. In fact, in 2018, production is about 6 million tons. And it ranks third, and it comprises about 8.3% of world aquaculture production in 2018. The first, of course, is still grass carp, and then you have silver carp, and then tilapia, the Nile tilapia. Okay. Tilapia is now emerging as a major industry globally. In fact, even in Brazil, in 2018, they have about 400,000 metric tons of production in Brazil. But of course, China is still the top producer of tilapia. Then we have Indonesia, Vietnam, Philippines, and Thailand, still among the top 10 producing countries. Okay. Tilapia is really produced in China, but China is also the biggest domestic consumption of tilapia. But you are blessed here in Thailand because you have many big hatcheries. In fact, some of the largest hatchery companies are in Thailand, and they are exporting fry to the entire region and other countries, neighboring countries. Here, you see the tilapia market. In 2020, the estimate was about 7.7 billion US dollars. Okay? But the projected market will be around 9.2 billion by 2027. Although there was a decrease in importation because of bad information, misinformation about tilapia, the US is still the #1 importing countries. And there is at present an increasing demand for frozen fish, frozen fillet. So we see here an increasing global market for tilapia. Again, we have Asian countries, Southeast Asian countries, including Indonesia, Philippines, Vietnam, and Thailand as exporting countries. I'll see if I can do, okay. Okay, tilapias in Southeast Asia. I think we're all aware that tilapia is not native to us. It is an introduced fish in Southeast Asia. Okay. Again, Thailand is so blessed. Way back then, the Emperor of Japan, a friend of your king, King Bhumibol, gifted Thailand Nilotica. And this fish was stocked in front of the palace, and it was named Chitralada strain. So you have the Chitralada strain. And before the gift came into being, the genetically improved farm tilapia, it was actually the Chitralada strain that was highly distributed in neighboring countries in Southeast Asia. We also got ours from Thailand in the early 70s. However, I think farmers were not very skillful in culturing tilapia. And eventually, again, through the years, there was this declining quality in our tilapia production in terms of growth. So fish became smaller. Okay. What could be the reason for this? In the ponds, the farmer would usually harvest the biggest fish and sell this in the market because it will command a higher price. So what's left in the ponds are small tilapia, and these are propagated again to produce the next generation of fish. And so eventually, we see this decline in growth. Okay. In the late, okay, closer. Okay. In the late 1980s, okay, selective breeding studies were initiated in Southeast Asia. There was this funding from Canada. The IDRC of Canada funded projects here in Thailand, the Philippines, and Indonesia. So it started the development of procedures for developing good quality tilapia. And in 1988, ICLARM, or what is now the World Fish, started a genetic improvement project in the Philippines. ICLARM networked with universities in the Philippines and also our Bureau of Fisheries and Aquatic Resources. Just a brief history of the genetically improved farm tilapia. The gift tilapia, what ICLARM did was to collect about 4 Asian Nile tilapia and then 4 African strains. And those strains were used as the base population, and further they did selective breeding. So you can see from this, all these many different, and there may be more that I'm not familiar with. Okay, so you have the Chitralada strain, okay. And then the PC Farm, okay, is a big company here in Thailand. They develop very good quality tilapia. They both have the Nile and the red tilapia. And here, you see here the world fish, that's a gift tilapia. This fish was highly dispersed in Southeast Asia, okay? In fact, most of the strains here that you see, except for the Philippine Sifdex strain, they were all derived from the gift fish, okay? There's Namsai fish, and in the Philippines, there were many derivatives also. The Philippine strain, okay, this was a strain I personally got from NIFI, from DOF. So I brought home, I was then working with Sifdec, and I was given Sifdec Fry, okay, by DOF, and I started working on the Sifdex strain. And somehow I never got to use the gift tilapia because we already had the tilapia strain based on the Citralada. So I did not bother to use the gift. And besides, it was research I was doing. I was in a research organization and I didn't have enough funding to pursue any kind of selection. Okay. So here you also have China. Okay. Again, fish were imported. I mean, the World Fish gave China the gift tilapia, but already in China they had Nile tilapia. Okay, so the gift tilapia wasn't the first tilapia in China. Now most of the hatcheries of tilapia in China, what they do is to hybridize the gift tilapia with Oreos niloticus. Okay, and because they wanted more males. Okay, of course they were doing selective breeding, and I think they had foreign company helping them. And so these are what we have right now. There may be more developed strain in the region. Thailand is also very fortunate. You have the Citralada strain, and you have many, many competent and well-trained geneticists. And most of them are consultants in your farms. Okay. So I don't foresee any problem, nuts problem here in Thailand as far as tilapia is concerned compared to other neighboring countries. Okay. I just have here a slide showing you all different types of hatcheries. This one is from the Philippines. It's an earthen pond hatchery. That's one of our famous mountain, Mount Makiling. These are from my studies, these upper ones, okay? And these pictures are taken from Namsai, okay? Courtesy of Mr. Warren, okay? And you see the importance of the hatcheries, it is an important link because the tilapia hatcheries actually, they are the provider. They provide and they need to provide a steady supply of fingerlings and juveniles for commercial farmers. Okay, so it's critical. Vital to the success of any tilapia hatchery is a proper broodstock management. Okay. This is a tilapia, in general, a tilapia industry chain. Okay. Well, we have usually the seed production, okay, and then you need to have a good broodstock management. Seed stocks are sold to hatcheries or to nurseries, okay? And then of course, this will go to grow out, big ponds. They can be in cages, they can be in ponds, okay? And different types of management system here. And this will go to post-harvest handling, upon harvest, okay? Then you have here processing, marketing, okay? In all these stages, we always find these guys. We have traders, we have middlemen, okay? They either go straight to the seed producers and buy seeds and sell them to hatcheries. So we always have this group, which actually I did not include in this loop, but they are very visible. And I guess even in Thailand, you have this, okay, the middlemen. So in general, this is what we have in the tilapia industry chain. Okay. I have here some real or perceived problems, but these problems may not exist here in Thailand. Okay? In general, this can be a problem with some of the countries growing tilapia. Again, The reason why I think this isn't much of a problem here in Thailand is because, again, you have good broodstock here, you have qualified geneticists, you have foreign consultants. So I guess some of this, to a certain degree, in some small hatcheries, may still experience this. But overall, I think you're doing well. Okay. Now, based on talks, informal talks with friends and people we've talked, I think this is your concern in Thailand. And I may be wrong, okay? I think at the moment, you're experiencing not very good market price, okay? So there may be an overproduction of tilapia, which is causing the price of tilapia, for example, to go down. You may not have an established processing plant. So if you have an overproduction, maybe post-harvest, there is no companies yet, and so it can be, well, it's a problem now, but I think it can be solved. And of course, we have diseases, okay? I think diseases is a problem, not only here in Thailand, but in practically in Southeast Asia and in most aquaculture setup when the environment is not very clean, when the environment is not good, okay? And when we do very high stocking densities, okay? You see pathogens, bacteria, they're always in the environment. They're always there. But then they become opportunistic when the immune system of the fish, for example, are lowered. Okay, so when there's overstocking, when you have so much feeding, you have pollution, then that's when this opportunistic bacteria are so happy. Okay, so they attack our fish. Okay, so I think in general, these are the major concerns here. And correct me later on, I may be wrong. Okay. What I have here is a flow of broodstock, or breeders as we call them, from primary producers to seed production, to the seed production systems. Okay. There can be other models for this. There are different ways of presenting it, but there is always that primary producer. Okay, we have this primary producer, and almost everybody buys from this primary producer. Okay. The thing is, only a small fraction of the population of fish is sold to hatcheries. Okay, there can be many hatcheries. Okay, these hatcheries in return, sometimes they become secondary producers. Okay, because they will also produce fish. They will use the fish they bought from the primary producer as their broodstock, okay? And they will sell to other farms, okay? So it's an informal network of the transfer of fish from a primary producer down to our farm. And even in farms, for example, they can use whatever they buy from the hatcheries and produce fish also, seed stock. And there may be cases where they will sell this back to the hatcheries, to the secondary hatcheries, or even to the primary hatcheries without those guys knowing that they're buying what they were selling before. And again, think of the middlemen, the traders. You know, they're very good at marketing, okay? So they can sell this, and there is a potential problem when that happens. So that kind of flow, that kind of informal networking happens. Okay. Okay. Okay, what I'm showing here are just the seed production systems, and I think you're more familiar with it than me. And I'm not going into the detail of this, but in most Asian countries, Southeast Asian countries, they usually have earthen ponds as hatcheries. They can be small, they can be big. It depends on the financial and the technical capability of the farmer. It can be just 2 hectares. It can be, so it really depends on the capability of the farmer. Okay. Hatcheries can also be done in cages in ponds. So while you have just a pure earthen pond, you can have hapas set in fine mesh, hapas set in ponds. Okay. This is easier to collect fry when you have, especially for producing future broodstock, when you have cages set in ponds. Okay. Cages can also be set in lakes. Okay. So we can have this in the Philippines. We have a lot of this. Okay. Now, when land is limited, okay, we can also produce fry in tanks. So tank production is practical when land is limited. Okay. However, this can be more expensive than maybe the other systems, unless, of course, the big ponds, because big earthen ponds are also quite expensive to develop. Okay. The advantage of doing hatchery in tanks is that you have a better control of your water quality and better management of the harvest of fry. So these are different systems with different variations, okay, and different advantages and disadvantages. Source of our broodstock. Okay. These are 3 general sources of our broodstock. Most of us in Southeast Asia obtained our first broodstock from research institutions, from the government, and from universities. In Thailand, I know that it's the DOF, the Department of Fisheries, is very supportive. You have, I don't know if you still have the National Inland Fisheries Institute, NIFI. Okay. You have NAGRI, okay. But in Thailand, for instance, you have your fish coming from DOF. Now, in general, in research institutions, we get our funding from government. So it's a public funding, okay. And usually, programs are set, okay. For the first 5 years, you work on this species, you work on this area. So scientists and researchers are mandated. Okay, so we have a budget for this. Okay, so we do research. Okay, so research is very strong in universities and research institutions. However, the downside of that is farmers cannot rely totally on research institutions for distributions, for example, of Nile tilapia fingerlings, because we don't have the facilities in the universities and research institutions to produce millions of fry or fingerlings. So there's a limited distribution. Okay? So in that sense, it's not sustainable. Okay? However, the very first founder population that were distributed to farmers, okay, and other interested parties all came from government. Okay. Now, it's working. Okay, then we have another source. We have producers. They can be biosecure, they can have biosafety, maybe some do not have. Okay. Now, again, depending on their financial capabilities, most of them, the nice thing about this is they appreciate research. They realize the importance of science, okay, so they continue doing research. So they also have their genetic improvement programs. And oftentimes, they hire consultants. Consultants can be foreign consultants or they can be local consultants. But there are always consultants available in big companies. Okay. So because they have this and they have the money, they can have a biosecure broodstock. Okay. They will also have the capability to monitor level of inbreeding, the word that we do not like in aquaculture, inbreeding. Okay? So they can do that. The downside is getting fish from them, buying from them, it is expensive. Okay? It comes with a price. Okay? You're buying biosecure fingerlings. Okay? Now, so these producers, they sell. Okay? Most of them, they protect their stock by selling only fry or fingerling to grow out or outside of the country. As much as possible, they don't want to sell to hatcheries who can copy their fish. And I think in Thailand, that is what's happening here. But in other places in Southeast Asia, when you sell to a hatchery, the hatchery will develop its own broodstock. Okay? So, hatcheries are also another source of broodstock. Okay? It is a perception that most are poorly managed. Poorly managed in the sense that they don't even know the history of the fish that they buy, the origin, the age perhaps, and they don't keep data. Okay, so there are information that they do not collect, and this information are very critical to management. Okay, they are also presumed to produce inbred seeds, especially remember the flow of fish that I showed you, especially if they use very few founder population, and we'll talk about that later, the effect of that. Now, the nice thing is, that's why many people buy from here, is they sell cheap. Cheaper than the biosecure producers. However, they may be selling copied broodstock. Copied in the sense that they think they can reproduce the good quality from these biosecure producers. But actually, in reality, they cannot. Okay, so they have no, they cannot offer biosecurity protection. Okay, so why do we need to do proper broodstock management? Okay, so we need batteries. Okay. Proper broodstock management is important. It is important because of consequence, negative consequence, for example. You have here, if you start with a small population, okay, which normally happens, okay, and this is sometimes a problem when you have, in aquatic species, we have very high fecundity. So you think that if you have, like, say, 3,000 broodstock, pieces of broodstock, you're already good, okay? But you're not aware, for example, that that only comes from very few parents, okay? So what is the problem with having small population? Okay. We have in genetics what we call genetic drift. Okay, I'll show a slide on this later. And once you have genetic drift, you also have inbreeding, okay? And the problem is you lose genetic variation, you lose diversity, you lose genes, you lose alleles. Now those are important alleles. Those alleles, those genes, may be what you need to adapt to a changing environment, for example, to changing climate. Okay. But then if you lose them in the system, there is no way you can get them back. Okay. So that is the danger of this small population. Now, inbreeding, we don't like inbreeding. Okay. Why? Because when you have inbreds, they die faster than non-inbreds in a bad environment. Perhaps if both the inbred and the non-inbred fish are in a good environment, then probably they'll have a better, similar survival rate. But in a bad environment, the inbred fish will not fare well, okay? It will die faster, okay? And there will also be an increased mortality from stress, okay? And even vulnerability to disease. So inbred fish will be more susceptible to diseases, okay? Another important thing to remember and why we need good management, broodstock management, is the many environmental pressures, okay? If it's possible for us to grow our fish in a water that we can drink, then that's very ideal. But of course, we know that we cannot do that. But we can minimize pollutants to our environment, okay? And, you know, when we stock too many fish, okay, overstocking is not good, okay? When we feed, you know, just like that, you know, no proper scheme of feeding is also not good because it will lead to bad water quality. Then when we have all these stresses, you'll have poor water quality, you end up getting diseases, and when the environment becomes eutrophic, meaning too much nutrients coming from the fish and also the feeds, then eventually we get fish kill. Okay. Okay. This is a slide that I have used in one of my talks in the Philippines when I was talking about the negative impact of aquaculture. Okay. Whenever we culture any fish, whether when we're growing fry, fingerling, or for grow out, we always have major inputs and outputs. And our major inputs, for example, we always have the seed stock, okay? We have our feeds and input, water, good water, and oxygen, okay? The surrounding area. So these are our three inputs. Our output, very important output, are these fish, big fish, okay? We don't realize that there are other outputs, okay? We have water flowing out, and with this water, you have dissolved waste. You see, coming into the cages or in the pond, you may have water and good oxygen level, okay? But we also have dissolved waste. In addition to that, there are uneaten feed. You have fecal matter, okay? These are also outputs. Solid waste, okay? These are output. And when this is too much for the system, we get eutrophication. And when you see this very green overgrowth of algae, eventually fish kill because we get low dissolved oxygen, okay? So I think it is important for us to balance, okay, growing our fish, whether fry to fingerling or fingerling to marketable size, and let us be aware of the environment. Okay. This is a slide that I use when I teach genetics in my class, okay? And when I talk about small population, how they become extinct. This is from a textbook, Campbell and Rees Biology. Okay, so we use this slide. This is an extinction vortex that goes spiral down. Okay, small hatcheries at some point will experience the extinction vortex. Okay, you see, when you have a small population, okay, what happens? You can have inbreeding, as I've shown earlier, and then you have random genetic drift. Okay, a result of this would be the loss of genetic variability, the loss of diversity. Okay. Now, when you have that, this leads to a reduction in fitness, reduction in the population's adaptability. So a population will have lesser chance of adapting to changing climate, okay, changing environment. Okay. And this can result to lower production, okay, and higher mortality. So you have this spiral downturn here, and then you have a smaller population. It becomes smaller and smaller unless something is done here, and eventually the population can collapse and become eventually extinct. So this is applicable not just to aquaculture species, but to many other organisms. Okay? So we call this the extinction vortex in small populations. Okay, so how can we break all this inbreeding problem in small hatcheries? There's no problem with big hatcheries because I think they're managing well. The only problem that I can perceive happening in big companies is when they do very, very high intensity of selection. You know, in selective breeding, when you have very high intensity, the meaning of that is you use very, very few fish, okay, meaning the best of the best. So there can be a narrowing, inadvertent narrowing of the gene pool, and that can lead to some kind of inbreeding. Okay? But in small hatcheries, inbreeding is most often a problem. Okay? So it's a big challenge. Okay? So what can we do? Okay? We can improve broodstock management. Okay? So there are ways of doing it, ways that farmers can do. Okay? We can also generate genetic diversities among small hatcheries by doing on-farm genetic improvement of different gene pools, okay, in different small hatcheries. When I was with CIFDEC, I did a study, and this study was published in Aquaculture Journal. I did a study with a farmer, okay. This small farmer, small hatchery, is just 2 hectares. He had cages in his ponds, and I developed a mating scheme for him to improve his growth rate of his fish. And in that study, after 1 generation of selection, we got 3% response to selection. So the farmer was happy with that. Like he was able to do the selection without disrupting the operations of his farm. Now, I was thinking when I did that study that if we can do that kind of genetic improvement in small farms, okay, that way they develop their own broodstock, maybe their own gene pool, okay, and even if they exchange resources among themselves, because hatcheries, they buy fish from each other, they exchange broodstock, then that way the broodstock they're buying are different from what they have. Okay, so we can do this kind of thing, like say in a big locality or in a province, if you can have like different local hatcheries, and if they produce their own, like they develop their own broodstock, then that way genetic diversity can be generated. Okay, and so we can link them together. And to my mind, that is one way we can break this inbreeding situation. But then I opted for early retirement from UP, from CIFDEC, and I joined the University of the Philippines to teach, and I wasn't able to pursue that dream of mine. But I know that some farmers that I've talked to, they're kind of doing it in ways, but they need guidance. Okay. Whenever we breed fish, we need to have a clear goal in mind. Okay, is your goal just to produce fry fingerlings? Okay, so you just purely produce them. So maybe you want large fingerlings with high survival. Okay, is your goal that, you know, like you're not selling to anybody, but you end up in your own grow out. Okay, so you probably want to have fish that are big fish like more than 800-gram fish for fillet, and you also, of course, want high survival, okay? Or you want to breed fish because you want future broodstock. Okay? For this talk, for this morning's talk, the remaining of the talk, I will focus on this broodstock management. Okay. Oh, yes, I will, but I'll show you 2 slides here why we want quality large-sized fingerlings. Okay, We want large-sized fingerlings because they will grow better and survive better in intensive production systems compared to small fish. Okay. Okay, this is a study, again, I did when I was with CIFDEC. At that time, the farmers were buying really the small fish, the fry, to grow in cages in Laguna Lake, okay, Laguna de Bay in the Philippines. And so I did a study where I had fish of different sizes. So I have here a size, an average weight about 2 grams, and the middle size I call the 8.9 grams, and a bigger size about 23 grams. They were all stocked at the same stocking densities in small cages. They were not fed because I grew them in the lake, okay? They were not given any feed. They just subsisted on the natural food, the phytoplankton. After 4 months, okay, and I sampled them monthly, okay? And we also took different environmental parameters. But after 4 months, well, monthly, it was consistent that the bigger fish were growing faster, okay? And at the end of 120 days, although this was leveling off, and the reason for this was that the phytoplankton in the lake was already being depleted because it was like summer almost done, and so we were getting rainy seasons. But they were all subjected to the same environmental conditions. And so it turned out that the big fish really grew better and with a high survival rate. Okay, so I was convincing farmers to use bigger size fingerlings for their grow out, but then they said that smaller fish are cheaper. Okay, so it's now a balance between buying a cheap fish because they're small and you can only grow that to a point, or rather than buy a bigger fingerlings. Okay, so we're talking now about traits. Okay, it is important to be aware and to record what traits we want when we want to produce future broodstock. So here I group them into economic traits and reproductive traits. Okay, so for economic traits, we are usually looking for good growth. You have disease resistance or disease tolerance or disease resilience. We want survival. We're looking at feed conversion ratio and color also. Okay, color is actually a qualitative trait, and all of this, the above, are all quantitative traits. Okay, but very important to consider also are the reproductive traits. Okay, especially when we are producing future broodstock. We need to know the fecundity of the fish. Of course, here we're talking about tilapia, but this applies to any other species. And you should know the size and the age of the breeders at maturity. At what size and what age do they mature? And of course, fertilization rate is important. Hatching rate of eggs is likewise important. Now, record keeping is critical. It is very important for management, future management decisions. Okay, I have listed down here some of the important ones that need to be collected by a farmer, and there can be others. Okay, so again, it is important to know the source and the age of your original breeders. Where did you get them? If possible, if you can identify the strain, so much the better. And then again, the size of the breeders, at what age, what size they mature. Because you will need that when you make decisions on replacing your breeders in the broodstock pond. Okay. And sometimes you have to consider also, if you don't have enough breeders, what proportion of the spawners need to be replaced. If you have a fish that even if it's only 1 year old and it's not giving you enough eggs, then it should be replaced. It should be removed. Okay? So still other important data. I did studies. Okay, these studies I did when I was already at the University of the Philippines, and we checked ovarian development. Okay, okay, in mouth brooding. Females, you all know, I think, that they mouth brood the eggs. It is important to know the timing when to remove the eggs. Some eggs are not ready to hatch, okay? So you need to be familiar with, for example, the color of the eggs, okay? Are these eggs, if you put them in artificial incubators, are they ready to hatch or not, okay? So removing the eggs from the mouth cavity of the tilapia also requires good timing, and you should know when to remove, okay? Measurements, okay. We need to do measurements. We don't just say that our fish is growing so and so, okay? When you don't have sophisticated equipment, like big companies have, we have weighing scales and rulers, okay? I was doing this with some graduate students, and you know the balance that we used because we were doing it in the field, you know the jewelry scale, you know the scale that jewelry stores have, okay? So you use that especially for small fry because we have to work in the field and we cannot bring our balance from the laboratory, so I decided to invest on jewelry. It worked for us, okay? Now, of course, big companies, they have sophisticated equipment. Now, it is important to do this because there is no way of knowing your fish is growing if you don't do measurements, okay? So we do sampling because research is important. You need to do research in the hatcheries. Even if it's a small hatchery, you don't have to design a complicated experiment, okay? There are simple experiments that can be done. And these experiments are critical for you to evaluate if your fish is really growing well or not, okay? Okay, stock management. We can do simple broodstock management, doable in farms, or nowadays, we can do DNA-based stock management, okay? Genomic stock management, DNA-based stock management is at an early stage. But in the future, this can be a routine procedure. And I am pretty sure that big companies are already into the DNA-based stock management. But it doesn't mean that because you don't have access to these molecular markers, then you don't do broodstock management. There are still simple broodstock management that can be done, especially in smaller farms. I've listed down here 4 major ones. Farmers can do more, okay? For example, there's the rotational mating that can be done. I did this with the farmer I worked with. The need for a high effective family size, okay? Broodfish exchange, meaning when do you get your broodstock out of the cages, and stock replacement, when do you replace your breeders? Okay. Okay. So this figure is modified from the paper of Kincaid. Okay. You can have here I have 3 lines, okay? Line A, line B, line C. You can have more, or you can have different families, okay? Now, what is done in rotational line crossing is you keep the female in the same container, maybe it is tank 1, okay? The female stays there every generation. It is the male, the partner of this guy here, that is moved to another tank. So the male here goes to this. So it's now mated with the female from B. The male from B is mated with the female from C. So the females stay, okay? They are not moved around, okay? So it is the males. Now, if you have like, say, 15 to 16 families or lines, it would take about 5 generations, okay, before the male and female here will meet. Okay, so this can minimize inbreeding. Okay, this minimizes inbreeding because you don't propagate the same pairs. So you move the males, you keep moving the males. Okay, the females stay here. So F1, the female is still here, and then so forth. Okay, so this is rotational line crossing. Okay, the need for a high effective population size. Now this is important because the choice of mature adults, meaning the fish that we use for spawning, is very important. It's a critical factor to consider. Okay? What we need to do is collect a large population to form the base population. And as I mentioned a while ago, in the gift, the genetically improved farm tilapia, that's the gift, okay? This was actually selected, but they collected first 4 Asian strains, okay, 4 African strains. And then after some generations, they started the selection. Okay. The population size, actually, is determined by the actual number of the parents that mate, rather than the total parental numbers in the pond. Okay, so we have this NE, or we call the effective population size. That is the actual number of fish that contributes to the next generation. Okay, it is not the total parental numbers unless, of course, you have an equal sex ratio. Now, why is this important? Why is the effective population size important? Because these are the fish that carry the gene pool of the population. Okay, so these are this group of fish that has whatever you want to transmit to the next generation. Okay? So what we need to do is to maximize the number of adults in spawning. Again, keep in mind that this is not to produce fry for production, for grow out, but this is to produce future broodstock. Okay, so we're talking about future broodstock here. Okay, so hatcheries broodstock should be kept to at least 50 pairs or 50 of the least numerous sex. Okay, and I will show you later why it is too important to keep it at least 50 pairs. If you can manage it, more pairs the better. Okay, NE, our effective population size, we can compute this by this simple formula. Okay, you need to know the number of males and the number of females. So just by using this formula here, you can actually compute, estimate your effective population size. Now, the best way to maintain a large NE is to spawn as many fish as possible. Okay, and I'll show you in the next following slides why NE is important. Okay, now why should fish farmers care about their NE? Okay, now this is important because of its relationship with inbreeding and genetic drift, what we discussed earlier. And when we know the effective population size, we can actually estimate the rate of inbreeding. This is the inbreeding coefficient that happens every generation. Okay, so the delta F, or the inbreeding coefficient, the increase in inbreeding, the rate of inbreeding, is given again by this simple formula. You need to know your NE. So how do you compute for your NE? You just need to count the number of males and the number of females. Okay, simple. Okay, so I'll show an example here. Talking here of the effect of sex ratio on NE. Okay, for production purposes, maybe 1:4, 1:5 is okay, but not when you are producing fish for future broodstock. Let's have an example. You have a population of 20 tilapia. And this 20 tilapia is made of 10 males and 10 females, okay? So if I use this formula, okay, and I substitute all the numbers, my effective population is also 20, is the same as the 20, okay? So what I have here, 20, that's the census population, meaning the total count, and that is also my NE, okay? Using same sex ratio. And if I want the rate of inbreeding, okay, then I know that my rate of inbreeding per generation is 0.025, okay. Now let me change the sex ratio, okay. Again, we still have 20, the total number of fish, but this time I reduce the males to 5 and the females 15, okay. Again, using the same formula, what I get now is 15. My effective population size is no longer 20. Okay, so only the 15 now will be involved in the actual spawning. Okay, and if I want to compute my inbreeding rate, I will get a higher inbreeding rate of 0.033 because I changed the sex ratio. Okay, so my sex ratio now is not equal, so more females than males. Okay. Now, okay. This is a formula. For you to be able to compute what kind of inbreeding rate you want in your system. Okay? This one is delta F. Sorry. You need, sorry about that. Okay. That delta should be there. Okay. It's, use this formula, 1/8 multiplied by your number of males and plus 1/8 multiplied by your number of females. Okay. Again, sorry about that. Okay. Okay. The delta should be before F. Okay. So this is how to compute or estimate your breeding coefficient every generation. Okay. Let's do some examples here. Sorry, I don't have a good, okay. Again, that's delta F. Okay. Yes, my math code is not working. Oh, okay. It's his fault. His fault, not mine. He's using a Mac. Okay. I was wondering. Okay. Now, here are some examples, a few examples. My number of male here is 3. Number of female is 3. They have equal sex ratio. Okay. So I have an inbreeding rate of 0.0833, okay, per generation. Okay. I have here 50 males and 50 females, okay? And my inbreeding rate is 0.0050 per generation, okay? Now, let me go to a higher number. I have here 25. I reduced the male to 25. I increased my female to 25. So I have here 75 females, 25 males, and my rate of inbreeding per generation is 0.0067, okay? You see, when you have a very small number, you have a really high inbreeding rate, okay? Now, this was what I suggested, that at least if you can keep your population, okay, at least 50 pairs, or 50 of the least numerous pairs, then you'll be, you'll have inbreeding, but your inbreeding rate is not going to be that high. Now, the value of F is between 0 and 1. The nearer you are to 1, the more inbreeding rate there is going to be. And the nearer you are to 0, the F is 0, the less inbreeding there is in the system. So we want F less than 1. Okay. Again, this one is a very nifty, it's a very useful formula because you can decide on the onset what inbreeding rate can you tolerate in your farm or would be acceptable to you in your farm, okay? Okay. So let's go back again to this small population. Why do I always keep on insisting about this happening in small population, okay? Because in genetics, again, we have this founder effects, okay? Now, when you have these founder effects, you have this reduced genetic Again, diversity. When the population, the new population, comes only from few parents. Okay. Okay. This is a slide that I also use in my genetics class. Okay. Think of these circles here as the gene pool, the genes. Okay. You have this black, you have that gray, and you have white. Now, our genes of organisms can exist in two forms. For example, you have two big letter A's. That's a homozygous. And in genetics, we say it's a dominant allele. Okay. We also have small letters. And again, in genetics, when you have the same letter, it's homozygous. But this one, when usually we designate small letters for recessive traits. Okay. But in the population also, you can have a genotype, okay? One big A and one small a, that's heterozygous. Meaning this individual here, for example, this would have the big A and the small a. Okay. Now what? Next. Okay. So what happens here? When, for example, you go to a producer, okay, primary producer, and hey, I want to buy fish, fry, okay, I'll sell to you, okay, and he will give you this portion, okay. He won't naturally, sometimes to protect their gains, they're not going to randomly get from the different families, okay. So they will not randomly get from the entire population. So they probably just give you a small portion, okay. So you don't know what you have, okay. So this one now is your new population, okay. In this new population, and if you look at these circles, okay, we don't have the white anymore, okay. So you lose that, okay. So, and even if you look at this frequency here, and we're not going to go into math here anyway, there is a change. We have reduced this. In the first place, in the beginning here, the initial frequency of the small alleles, the homozygous allele, is already low, 0.16. But after the founder effects, after the small population, in the founder effect, you now have a very much reduced. Okay. Now, why is that critical? Okay. When you lose alleles, okay, whatever you lose in the system, you cannot regain them again. Okay. You cannot get it back. Okay, I want this. Okay. Now, the alleles that may be lost in the population, perhaps they are the genes that are needed to adapt to climate change. We never know. And that is the reason why, as much as possible, we always want to have a genetic variability in our population. Okay? As much as possible, we don't want to lose alleles. We don't want to lose genes. With this changing climate that we have now, it is critical that we have high genetic variability. Some of the genes, some of the alleles that we lose in the system may be the alleles that we need in the future to deal with many perturbances in our environment. Okay? So that's it. And when you have the genetic drift, it can severely change the genetic variability by generations. Oops, sorry, that's wrong. Generations. Okay, wrong spelling. Okay. And when you have genetic drift, the problem also is that you limit future genetic improvement. Okay. One cannot do, no matter how good a geneticist you are, if there is no genetic variability in the population, you cannot do any kind of genetic improvement. There can be no gains, okay, if you have no genetic diversity in the system. So it limits future genetic improvement, okay? And this does not lead to adaptation. As I mentioned a while ago, if you lose alleles that are needed for adaptation, then there's a big problem in the system. This is also again to illustrate. Now what I have here is bottleneck effect. Okay. Remember, we always get floods. Okay, sometimes our ponds are flooded. Okay, we lose lots of fish. Again, I use in my class. Okay, so supposing before a storm, okay, and in your pond, again, you have all these different genes, okay, and you have big flooding, okay, all the fish, many of them are lost, but a few remain, okay? So we have here the survivors, okay, in that catastrophe. Now, if you look at this is not a representation of the former ones, okay? There's a bottleneck. It's like when you have this big bottle and you put all the coin or the marbles inside, and when you pour, you only get so much, a few, okay? So the resulting gene pool here is no longer reflective of the original gene population. And this bottleneck effect happens when there are catastrophes, okay? When a population is reduced because of certain events, random events. Okay, so going back to our favorite word, inbreeding, okay? Inbreeding happens when you mate closely related individuals, when they share the same grandfather, grandmother, okay, the same ancestry, and this usually happens in small population size. And we don't like inbreeding. We are concerned because of this, because of inbreeding depression, okay? Which is simply the loss of fitness, meaning these are some of the things that manifest when there is inbreeding depression. This may not be obvious immediately or all of them, okay? But slowly, through several generations of inbreeding, you will eventually experience poor growth, maybe high mortality, and then your fish getting sick, and you get all these kinds of abnormalities. So to avoid this, to minimize, because we can never avoid inbreeding in a closed system, in hatchery system, which will always somehow be at a small size, okay? But we want to avoid, we want to minimize, and we do that by avoiding inbreeding during broodstock development. We start with broodstock development. If your broodstock is not good, then no matter you spawn thousands of breeders, your seed stock will not be good. Okay. We need to practice good genetic practices. Okay, this is important. Now, most of the things that I mentioned, they are genetics in nature. I cannot label my talk as genetics because it's supposed to be on broodstock development, management, but genetics is an important component of broodstock development. Okay, you see, large effective population size, and we discussed that, the RNE. Equalizing family size, okay? You need to have equal males, females. Then, the systematic subline crossing, the rotational crossing, okay? But you have to be careful here. Do not mix different lines in one pond. Unless, of course, you can physically tag them and you know that this belongs to line A, this is to line B, line C, okay? As much as possible, if you do not have the capability to tag them properly, put them in separate ponds. Okay? And crossbreeding. Okay? Crossbreeding, when the heritability is low, okay, crossbreeding is more efficient than selection. Crossbreeding is a fast way of minimizing inbreeding. However, we need to be careful because when you do crossbreeding, you may be transferring genes to your system that is not good. And the thing is, you will only find out later. Okay. The thing also to remember is the difference between crossbreeding and, for example, hybridization. Crossbreeding is we cross strains of different of the same species. Okay, for example, in Nile tilapia, okay, or Euchromis niloticus, then you have a Thailand strain, you have an Israel strain. If you cross them, that is crossbreeding. So crossing different strains from the same species. Hybridization is a little different. Okay, you cross two different species. For instance, crossing Oreochromis niloticus with Oreochromis aureus, okay? Or Oreochromis niloticus with Oreochromis mosambicus. And you have that objective in mind. The objective of doing hybridization is you want a specific trait. You want the best of both traits, okay? So you're looking after what we call heterosis in genetics, meaning the F1 is better than any of the parents. But the thing to remember is that you need to keep on maintaining your parental stock, okay? If you do hybridization, you need to have the parental stock because your F1, you cannot use that as parents for F2 thinking that you will get the same advantage as your F1. Okay, some people think that when they have the F1 and they cross that with F1, their F2 will be performing as best as the F1. No. Okay, so there can be a breakdown in the F2s. Okay, so I just need to emphasize that. Okay, brood fish exchange. Okay, this is also one breeding management practice that is good. Again, the removal of eggs, okay, or yolk sac fry from the mouth of females, and this increases spawning frequency of your fish. This can minimize cannibalism, okay, and this also allows females to rest. Okay, females are mouth brooding, and when they are mouth brooding, the eggs, even the fry in their mouth, they do that about 10 to 12 days, and they do not eat. Okay, so they become very slender, okay, and it's not good for their gonads. Okay, so what happens here is you allow them to grow, okay, you allow them to be healthy. Okay, stock replacement, you also need to know when you replace fish. And in tilapia in the Philippines, we do this around 1.5 to 2 years old. Okay, so this good breeding management, okay, again, you breed from a large base founding population, okay? You can grow your fish using efficient husbandry techniques. You can do selective breeding. You sustain genetic gains by minimizing inbreeding. But the important thing to do is to monitor inbreeding in the hatchery stocks, okay? And this one is a diagram of hatcheries, nurseries, traders, grow out, okay? Okay, the benefits of good broodstock management, everybody is happy in the food chain, okay? So you see all these positive things happening, okay? And including the grow out, the processor, everybody involved in the tilapia chain, okay, is happy when you have good management. So why is genetics relevant to aquaculture? Okay, not just to sustain fish production, but the bottom line is dollars. Okay. And my last slide, yes, my recommendations for sustainable tilapia seed production. You need to do the best hatchery practices. You have to do proper broodstock management, observe sound genetic principles, minimize inbreeding level, and use efficient feeds so you don't pollute the environment. And kapkun.